Imagine you have this alkene and your task is to determine whether it is E-isomer or the Z-isomer. How would you do it? Because the molecular formula is identical, the bond connectivity is identical. Therefore, Proton NMR spectrum splitting pattern will be identical for both the molecules, and the chemical shift value will not provide you a definitive answer. So how do chemists solve the stereochemical mystery? The answer lies in 2D NMR techniques, particularly COSY and NOESY NMR. At first glance, you might think COSY NMR should be able to distinguish between these two isomers. However, in this particular case, COSY fails completely. Why? Because COSY only tells us which protons are connected through bonds. It means they gives only Wisnel cross coupling, and you can see the 4 bond coupling as well, but those will be weak, and therefore the information is identical for both the E and Z isomers. So if COSY cannot help us, what can? This is where NOESY NMR becomes incredibly powerful. Unlike COSY, NOESY does not look through the bonds, it looks through the space. It tells us which protons are physically close to each other in the three-dimensional space. And as you will see in this example, a single noisy cross peak is enough to reveal the correct stereochemistry and solve the EZ mystery. So let's dive into the spectra and see how it works.
Okay, so this is the IUPAC name of this molecule, and this is the 1H NMR of this molecule, and this is the NOESY NMR. Before jumping to the NOESY NMR, let's assign the each signal of the proton NMR. First, I have given the number to each proton. So the acetylene proton is number 1 proton, this methyl is 2, this one is 3, and this CH2 is 4th, and hydroxy proton is 5th. This numbering is just taken randomly. This is not based on the IUPAC. Okay, so the first peak is belongs to the second proton of the methyl, this one, and this broad signal is belongs to the hydroxy proton. This sharp signal, which is singlet, is belongs to the this one proton, and this one is belongs to the fourth proton. And why it is doublet? Because of the splitting by this 3 proton. Okay, this 3 proton is splitting this one into the doublet, and the last one is this 3 proton, which is triplet because it's splitting by the fourth proton. So now we have assigned the proton NMR of this molecule, but this molecule actually existing into two isomers. So one is Z-isomer and another is E-isomers. In Z-isomers, the CH2OH and acetylene are on the same side, and in this case are on the opposite side. So 1H NMR of both the molecules will have the same splitting pattern. As I have already explained you that the chemical shift value will be either closer. You cannot explicitly say that this 1.9 ppm methyl signal belongs to these Z isomers or belongs to the E isomers. We don't know exact chemical shift value for this Z methyl or the methyl of the E isomers. Therefore, we need 2D NMR techniques to distinguish them. So can you distinguish them by COSY NMR? So the answer is no, because COSY NMR gives 1H correlation through the bonds, and the strong peaks comes due to the interaction of Wisnel protons. And if you see here, Wisnel protons are this one. Okay, so you will see the interaction of this one, but in the E isomers is also there, right? And hence you cannot distinguish by COSY NMR. If you talk about the 4 bond coupling, then it is very difficult to see the 4th bond coupling. A 4th bond coupling is like 1, here 2, this is 3, and then this hydrogen of methyl will be 4th bond, right? If you see, let's say, imagine you are seeing the 4th bond coupling, but here is also this will be the 4th bond coupling, like 3, and this methyl hydrogen is the 4th bond. So it is clear that whether it is 3-bond coupling or 4-bond coupling, you cannot distinguish by COSY NMR. Now the question comes, NOESY NMR. How can you distinguish them? Because NOESY NMR also gives 1s interaction, but this is through the space. Therefore, only those protons will show the interaction which are in close proximity in the space up to 5 angstrom. So if it is Z-isomers, so you must see the interaction of the fourth proton with the one proton. Okay, and 3 proton interaction of the 3 proton with the 2 proton. But if it is E-isomers, then fourth proton will show the interaction with the 2 proton of the methyl. Okay, or 3 proton will show the interaction with the acetylene proton. Okay, so it is very clear that NOESY NMR will be different for both the isomers. Now it is time to interpret NOESY NMR. So this is the NOESY NMR. This is x-axis proton NMR in the x-axis. This is proton NMR in the y-axis. Okay, so NOESY NMR is also symmetrical around the diagonal, exactly similar to the COSY NMR. Okay, so before interpreting, let's assign each signal of the proton NMR. Now you are seeing the diagonal peaks and the cross peaks. I have already explained in my previous video. You can watch my previous video. I will provide in the comment box what is the significance of the diagonal peaks and the cross peaks in a detail. I have explained in detail. So again, I will say you in a very briefly that these diagonal peaks represent the chemical shift value of the proton. You can see that this is here diagonal peaks belongs to this proton, and this diagonal peaks belongs to the 5OH. So similarly, there should be 5 diagonal peaks, right? 1, 2, 3, 4, 5, because there are 5 types of protons. Okay, these diagonal peaks are not very significant. See, the main important peaks are the cross peaks. Now let's look at this cross peak. So this cross peaks is arising due to the interaction of the fourth proton. How to interpret this is, you can draw the vertical line and then horizontal line, and you can see that where they are matching. So it is matching to it is connecting fourth to fifth. So you are seeing this interaction. Okay, this interaction. Okay, this molecule E-isomer will also show this interaction, and hence we cannot distinguish just by this peak. Okay, let's look at this peak. This peak is arising due to the interaction of the 3 with the 4th. Okay, where is the 3 proton? This is the 3 proton and 4th. So it means this interaction, right? And this interaction will be here. Okay, so still we could not distinguish this molecule, but still one peak is left, this one. Okay, this peak is arising due to the interaction of 3 with the 2 proton. Okay, let me make it bold. Okay, 3 with the 2. Now this is the 3 and this is the 2, and we were looking for this single cross peak. Yeah, look, this single cross peak is enough to distinguish between Z and E isomers. Now we can clearly say that this NOESY NMR belongs to the Z isomers, because we found this interaction. And you didn't find the interaction of fourth proton with the 2. Okay, where is the fourth? This is the fourth. Do you see the interaction of fourth with the 2? No. If it was E isomers, you must see the cross peak here. I am making another cross peak just to explain you. This should be for the E isomers if it was E isomers, but we don't have E isomers, but we have Z isomer. These peaks differentiate the Z isomers. Now we have understood that this molecules has Z stereochemistry, but story didn't end here, because I was also expecting that this fourth proton is in close proximity to the 1, right? But is not showing any cross peak here, right? I was expecting this cross peak. Please note down that I was expecting this cross peak because of the fourth proton interaction with the 1, but I didn't see why. This question comes into my mind. Therefore, I decided to draw this molecule into Avogadro software and check the distance between 4 and 1. So let's see the Avogadro software now. Okay, so this is the molecule, but this is not in the minimum energy state. So I'm going to make it into the to minimize the energies. Now it is going to occupy the orientation which is more stable. Okay, so as you can see that Z isomer Z structure is the more stable. Okay, now I'm going to stop it. Okay, let me give the rotation. Okay, as you can see there, this is there is hydroxy proton. This is the 2 CH2, and I want to see the interaction of this CH2 with this hydrogen, right? So I'm going to measure the distance. I have selected this tool, and I'm going to select this atom and this one. Okay, so as you can see, the distance is 4.233 angstrom, which is still under 5 angstrom, right? Okay, now let's measure this distance, this alkene carbon with this methyl. Okay, so this distance is 2.33 angstrom. So now I understand that why I didn't see the noisy of this proton. You know why? Because noisy is inversely proportional to the distance raised to power 6. Okay, so as the distance became double, here it was 4.2 angstrom, right? It became double, and here it is 2 angstrom. So when the distance became double, so noisy effects became 64 times less, right? Because it is raised to power 6, so it becomes 64 times less. So what I understand that if you want to see the noisy effect, if you want to see the cross peak in the noisy spectra, then the distance must be between 2 to 3 angstrom. If it is above the 3 angstrom, then you see the moderate. If it is above the 3 angstrom, then you might not see any interaction.
So that's all for today. I hope you find this explanation helpful, and I hope you understand how to use the NOESY NMR to distinguish between the geometrical isomers. And in my previous video, I used the NOESY NMR to distinguish between the regioisomers. So we will see you in another video with the new NMR challenge. Till then, take care, bye bye, and don't forget to subscribe to my channel.